So, says the position of a particle traveling along a straight line is given by x of t equals t cubed minus, okay, some crazy big function. So we've got some particle and it's moving along a straight line. You know, it's kind of doing one of these, right? And I'm only kind of drawing above because I want you to be able to see where I'm drawing, right? But ultimately it's staying right here on this line and just kind of moving back and forth. All right. And that's the function that kind of determines the position of the function or of the particle. So it tells us where it is on that number line. Is it at 2? Is it at 3? Is it at -5? We don't know. And then it says on the interval t equals 0 to t equals 10, when is the particle farthest to the left? When is the particle farthest to the left? Okay, so what does that mean? What are we looking for? What would this look like? Ariana? You threw a hand. Go. You got to unmute.
I'm so sorry.
No worries.
So when it says farthest to the left, I imagine that our output wants the greatest negative value we can find.
Greatest negative output. I love that. So you're saying we were looking for when it's farthest that way. We're looking for the greatest negative output. Somebody say that differently because synonyms really help us here.
The smallest number.
Smallest, yeah, we're looking for the smallest number. Okay? Somebody say it differently. Okay, so think about this. What does this thing look like? We don't have to be perfect, right? But it's a graph, right? Yeah, it does. I see some people kind of tracing it, and we don't know what it looks like. We do know it doesn't have that many humps, but you know, something like this. And so what we're really looking at is for like the smallest, you know, or the greatest negative output, the smallest output, right? We're looking for a minimum. So think about those spots that I just kind of circled, or at least one of them. Yeah, Joe.
That looks like a relative minimum to me.
Sure.
Which is a directional change.
Direction change.
Which gives me the implication that our first step could be to find the derivative of the function.
Why?
Because when we find the derivative of the function and we set it equal to 0, that means that there is a potential direction change.
I love that. Potential direction change. And I don't know why I abbreviated PDC. It's just fun. So if the derivative equals 0, if we have a horizontal tangent, right, derivative equals 0, we have a potential direction change. Is there any other way the direction could change? Could the graph have looked any different for us to still get something that's going here and then something that's going there, besides having a horizontal tangent?
It could be where it's non-differentiable.
Right. So we might have had it, you know, undefined. Now, in this case, is this something we have to be concerned with? No, it's a cubic function. That's differentiable everywhere, right? Like those are smooth. They don't have any crazy weird slope changes. There's no discontinuities. So in this case, we don't have to worry about it. But foreshadowing, anytime we're looking for potential direction changes, we're really looking for when does the derivative equal 0 or when is the derivative undefined. Okay, so that's what we're looking for here. Okay, so let's go ahead and do that. I mean, this isn't hard for us to do. Love the notice how we use synonyms a lot. So x prime of t equals 3t squared, subtract 18t plus 15. Now keep in mind, what is this x prime of t function actually giving us, just so we can make more connections? What is this telling us about? What? Go ahead.
The velocity.
Yeah, this is really telling us about our velocity. So when we're saying we want to find a potential direction change, we're finding when the velocity was 0, because that's when it could have turned around. And we've seen that in class. So now we know we don't have to worry about that one because it's not going to happen. So we just want to figure out when does this thing equal 0. Things that I notice, there's a factor of 3 in them all. So I would pull that out right away, right? And that would leave us with t squared, subtract 6t, add 5. When I do this, I instantly notice that I can factor it into t subtract 2. Oh, wait, no. Ugh. T subtract 1 and t subtract 5. I was thinking 2, 3. I was thinking backwards. So what this means for us is x equals 1 and x equals 5 are really those potential direction changes. Okay? So now I want to know which one's furthest to the left. How might I figure out, right? Because these are the spots that we're interested in. Those are the x values, even on our original graph, and I'm trying to kind of use colors here. Blue for the original and yellow for our derivatives. Those are the spots when we have a potential direction change. How do I figure out which one's furthest to the left? Not Joe? Someone else? Yes, Jade?
So I was thinking that if you found the y values of that, it could tell you when it's most negative, because we're looking for like farthest to the left, but in this case that's going to be like whatever y value is most negative.
So you're saying just find the y values, Painter. Just find the outputs. God, 7 minutes until you're in. So we could do that. Does anybody have any other thoughts? We could have also done like, that whole number line assessment, right? Like I really am looking at an x value of 1 and an x value of 5, and I'm really wondering which way it was moving. So, what was x prime of t before, after, and, so we could really be looking for when was the function going down, and then all of a sudden the function went up. So when was the derivative negative and it changed to positive? Because that's going to signify for us a minimum. But I like Jade's idea better. Jade.
So for the x equals 1 and x equals 5, can you change that to t?
Oh, yeah, my bad.
It's like messing with my head. Sorry.
No, that's not something you should be sorry for. I should be not messing with my variables. So what I would do at this point is I would do what Jade suggested, and I would just go ahead and plug those in and find the y values, which isn't too bad, and whichever one gives us the greatest negative. There is one thing we have to be careful of. Okay? One thing we have to be careful of, and I'm going to come over here and kind of show it. Notice it told us on the interval 0 to 10, right? So think about what the graph could have looked like. What if, 0 is definitely there. What if 10 was over here? Where does it have the greatest negative value? Where's the particle furthest to the left? I see it. I don't see the issue. Jenna, where is it furthest to the left?
Like, down by the 10, it just keeps going. So you don't really know what that point is.
So, in other words, if you go back to what Joe said in the beginning, he said, we really want to find those potential direction changes, right? Because that's where we might have a minimum or a maximum. But when we're looking on an interval, we've got to check the ends of the interval too. So really, the points that we need to check when t equals 1, when t equals 5, we need to check when t equals 0 and t equals 10, because in theory, it doesn't have to happen at one of those local minimums. It could have actually been going downward and hit it right at one of the ends of our intervals too. I see that idea. I don't see that idea. Jade, you're a kind of?
Yeah, I guess I see why we need to find the t equals 10, because if the graph did look like that, then obviously that would be the most negative y value. But I'm still wondering, maximums and minimums, did we find those just because that would be where they change direction?
Yes.
Okay.
And ultimately, because might it have been possible that 10 was right here?
Yeah.
And if that was the case, where would the most negative spot have been?
At the relative minimum.
And so ultimately what we're saying is if you're trying to find the most negative or even the most positive spot, yes, you need to look at those direction change spots, the local mins and maxes, but you also need to look at your endpoints of your interval. And that's only true when we have an interval, right? This kind of complicated the problem for us. And we're going to return to this more and more and more. Like, as a matter of fact, in next unit, we're going to be looking at finding absolute or maxes and mins on intervals for sure, formally. So this is kind of a foreshadowing. But again, I don't think this problem is beyond us at this point, right? We're just using what we know. So when we get here, it's going to go quicker. And that's okay.